But of morning, where are the people? I was waiting to admit you waiting for guys, but I don't see them. Let me give them 3 minutes. It's 9:15, we get started. Let me try to reach them on WhatsApp.
Nkubuulira ate kiki ekiddako. Sirina ssente ezimala okukola byonna eggwanga lye bineetaagisa okukola. Omanyi Omuganda agamba nti bw'otafiirwa tofuna. Abali mu kintu ekyo ekizibu ekyo abantu bannannyini masomero. Nze amagezi kati mpa amagezi ng'omuntu ayasoma bizinesi. Bwe banaaba balinawo aseti endala bagitunde. Kati ssente zinaava mu aseti ziri zijje zikozebwa. Okusinga abo gw'onoofiirwa byombiriri esukulu bagitunde ne kabe kasinge n'eri aseti eyinza okukwatibwako naddala ng'oba wagisingayo mu banka. So bwe tutyo bwe tulina okukola. Minisita Matia Kasaija ow'ebyensimbi ng'awa amagezi eri bannyini masomero ebintu mulabe engeri bwe mubikuba ebbeeyi musobole okufuna ku kasente akabavuumisa amabanja. Mu studio wendi n'omubaka Yusuf Kuzisi Makula nakasekeesawo tusebe webale kujja. Ku line tulinayo Mwami Kaweesa Kiwanuka Christophe ompulira bulungi. Tuwuliziganye. Webale kutwegattako ssebo. Okay, Mwami Kaweesa Kiwanuka oyo y'omu.
Okay, Matov, I think people are still oversleeping. I went out, jogged, and I'm back. But now, since those people are oversleeping, for us, let us continue. So we had introduced work, power, and energy, and we had talked about work done earlier. Any concerns of work done before I can proceed? Any concerns that you have, if I can proceed for work done? So you will find that we had reviewed. This was under work, power, and the energy. And we had already talked about work done as force times distance. We talked about work. There are different work done. There is work done against gravity. We talked about work done. He has gone off. Why is network? Okay, he's back. Brian, your network is not good. Eh? Work done against gravity. And this work done was the measure of gravitational potential energy. This was the same as gravitational potential energy. Then we also did work as a result of kinetic energy. Work done against friction. So work done due to a body moving was equal to work done against friction, which is WF is equal to the frictional force times the distance. We overcome friction. Then the other kind of work done is the work you do when the body has a given velocity, which is the measure of kinetic energy. This is work done due to moving bodies. And this work done is what we call kinetic energy, which is equal to 1/2 mv squared. From that work done of moving bodies, we can get what we call the work energy theorem. The work energy theorem. Remember, I sent the notes earlier, and the work energy theorem states that the work done by the resultant force is equal to the change in kinetic energy. And they can ask you to derive that to show that actually work done by the resultant force is equal to change in kinetic energy. And that can be done using the equations of motion, which is the third equation of motion, which is equal to v squared is equal to u squared plus 2as. And in this sense, you will discover that v squared minus u squared is going to be equal to 2as, which is the same as v squared minus u squared divided by 2 is equal to as, where v is the final velocity with which the body is moving, u is the initial velocity with which the body was moving earlier. So introduce a useful mass on both sides, and we shall have from v squared over 2 minus u squared over 2, this will give us as. If I multiply both sides by m throughout, we shall realize 1/2 m v squared minus 1/2 m u squared is going to be equal to mas. Now this is the change in kinetic energy, which change is going to be equal to mass times acceleration is force, which force is multiplying distance, and mass times acceleration is the resultant force. So for that reason, the work done by the resultant force is equal to the change in the kinetic energy of the body. So with that, you would have stated the theorem, and at the same time, you would have derived the equation which brings about the theorem. So if the question says, state the work energy theorem, 3 marks or 4 marks, one, they need you to state the theorem itself, and then they will also require you to go ahead and derive the theorem and show us that you know exactly how this theorem comes about. Okay. Then the other bit also I had to share with you is the bit of knowing the other bit can be got from what if a body is on an incline? If a body is on an incline, these are the conditions or the types of work done that the body is going to possess. One, if the body is down and it is pushed to go upwards with a velocity v, and this body goes and stops here. This was point A, stops at point B, but there is friction, it is overcoming. This body also experiences a normal reaction R. It has its weight mg, it is going to rise through a height h, then it is going to move a distance x along the plane. So the distance x is the distance we move while overcoming frictional force. So for that reason, this h will be equal to x sine of theta using Pythagoras theorem. If I extract out the triangle, which is right angled, then this would be my h, this would be my theta, this would be my x. This will be x cos theta downwards. Then opposite will be x sine of what? Theta. Now, when bodies are moving in that sense, at A, the body possesses only kinetic energy, which is a half mv squared. It has 0 potential energy. At B, the body possesses potential energy, which is mgh, which is the same as mg x sine of theta. The kinetic energy at B is 0 if the body has stopped. Yeah, but as it was going, that is between A and B, the body was overcoming frictional force. So because the body was overcoming frictional force between A and B, then we need to go ahead and get the work done against frictional force using whatever we have on that incline. So the frictional force is on the inclined plane, and this body is going to move a distance of x trying to overcome the frictional force. So for that reason, we can say between A and B, work done against friction is going to be W dF is going to be equal to the frictional force times x. But remember, frictional force is got from mu r times x. If frictional force is mu r times x, then what is r? When a body is on an incline, the normal reaction is a resolution of the weight. And this is always mg cosine of theta. So therefore, we shall have our work done against friction as equal to mg cos of theta as our r times mu times x. So finally, the work done against friction is mg cos theta mu of x. Okay, this is in brackets, but I can best write it as mg mu x cosine of theta as our work done against frictional force. So that is when the body is on an inclined plane. Now, we had discussed a lot of this in terms of work done. Now, we had not yet talked about energy. Energy, definition of energy. Energy ideally is work done. Yeah. So if energy is work done, energy is the ability to do work, or the capacity to do work. If you go ahead, what do you do in the morning? For example, what do you do in the morning? Me, I wake up, I go jog. When I go and jog, I'm doing work. But the amount of work I've done describes the amount of energy I possess. If I jog 1 kilometer, that's the energy I have. If I jog 2 kilometers, that's the energy I possess. If I jog 3 kilometers, that is the capacity of the jogging I can do. The work I'm doing is jogging. If I jog 10 kilometers, that is the energy I possess. That is the ability of doing work that I have. So energy is the ability to do work. From that, I've already stated the work energy theorem is what we call the principle of energy. Principle of energy. These 3 items, these confuse people. The principle of energy states that energy is neither created nor destroyed, but it can be transformed from one form to another. So first of all, we do not know where the energy comes from, but we know it is there. We cannot also say energy stops here. But what we can do, we can transform the energy from one form to the other. Why? Because it can neither be created nor can it be destroyed. Energy is always there. It is continuous. I always give this example. Listen to it very carefully. The sun possesses energy as it burns off hydrogen photons. When it is burning, it gives out light energy, which light energy comes to the earth. It takes around 8 minutes to reach the earth. When the light reaches the earth, the plants absorb the sunlight as energy, and they use it to do what? To make their own food. Then the food the plants make, they convert it into another form of energy, which bears flowers and then fruits. And what happens? We humans and animals run to those flowers and we eat that energy. Remember, the energy came from the sun as light. They converted it into food for plants. Further, you converted it into food and flowers, which are supposed to be eaten by humans. Now humans are eating the food. They are converting the energy. From the food, we are eating the food, you eat the food, you grow big, you grow up, you're converting all the energy into that. You get the energy to walk, the energy to run, the energy to perform any other tasks. But not knowing, some people don't even realize that that energy is coming from plants. That is why when we are measuring the radioactivity of human beings, we need to measure the carbon content because we eat a lot of carbon. Carbon comes from plants because plants absorb carbon dioxide. So they convert the carbon into the fruits and the foods we eat. Then we eat a lot of carbon. So our bodies are made up of so many components of carbon. So that's why when they're measuring our radioactivity, they measure the carbon content. So we eat the food, we grow up, we convert the energy in other items, we die. We die, convert the carbon back to the soil, add nutrients to the soil. Yeah, other plants grow, other human beings eat it. It is a continuous up to infinity. We don't know when it will stop, but we found it existing. That is why you can say energy has been there. It is never created. It will always be there. You can't destroy it. It just transforms from one form to another. Another key example I can give you is electricity. Electricity, when we went to visit the dam, the engineers there, we asked them, but can we have a day without power in Uganda? The engineer laughed and said, really? He said, as long as we have the River Nile, we have power in the whole of the country. We're like, what? How come we have challenges? Like, those are transmissions and distribution problems. But we at the source, we at the dam, we produce power every single minute. And we can never shut down. I'm like, wow. I'm like, why? He said, as long as the water is there, the water is the power. That was a very interesting physics statement. And if the water is the power, do you know what he meant? The river water is running. It possesses energy, kinetic perhaps, because it has a velocity. They dig a dam as far as like below 8 floors. That's where the turbines were. The water comes from the top there, drops where down the turbines are, drops at a given height, so it gains the potential energy. Yeah, so its mechanical energy increases. That mechanical energy of the water is converted into the mechanical energy which runs the turbines. Then the turbines convert the mechanical energy into electrical energy. Then the electrical energy produces for us what you call electricity. Then electricity is transmitted. When it is being transmitted by those wires are performing work, they are doing work, they are transmitting power until they reach where we are. That is why I can have this light, the energy now, which was water initially. Energy possessed by water has been converted into this light that is enabling you to see me. It has been converted into energy that displays images on TV screens, that displays images on your computer, on your phone. And what happens? You get the message. That energy is converted into electrical, then from electrical to electromagnetic waves, then from waves into your ears. Then they go as messages to your brain. Then you understand the concepts. All that is conservation and conversion of energy. We started from the dam, from the water. So always energy is transformed from one form to another. You cannot stop and say, this is where the light stops. No way. The light can shine, but it keeps traveling. You don't know where it goes. So energy is continuous. Energy is neither created nor destroyed. Then the other item is the principle of conservation of mechanical energy. Now, this principle states that if no external forces act on a system, the total energy before is equal to the total energy after. Then other people can say, in a closed system, total energy before is equal to total energy after. But I can summarize all those statements by saying, in a closed system, total energy is a constant. In a closed system, it means there are no external forces acting. Is a constant, it means the energy before is the same as the energy what? After. Right? Now they can ask you for the proof of the principle of conservation of mechanical energy. They can ask you to prove that or to derive an expression that can confirm that actually total energy before is always equal to total energy after. In that sense, we can consider if you want to prove this, we can assume we have a body initially down here, where initial height is 0, but initial velocity is u. Then this body rises and reaches point B, where the height is h, capital. The speed attained here is v. So at A, the body possesses only kinetic energy because potential is, which is supposed to be mgh, is 0 because h is what? H is 0. Then at A, it has kinetic energy, which is equal to R half mu squared. Therefore, total energy at A is going to be R half mu squared, and this is equation 1. When you come to point B, at point B, the particle has risen up a distance capital H, so it possesses potential at B, which is mg capital H. Then it also has kinetic energy at B, which is going to be got from R half mv squared. So it is equation 3. So for that reason, that is the case, then total energy at B can be got from mg capital H plus R half mv squared. Then if you go ahead and use equations of motion, whereby v squared is equal to u squared plus 2as. Then when this body is going up, the acceleration is covering is acceleration due to gravity, and it is a negative because the body is going against the attractive pull of the earth, right? So I think you know why G is always negative when the body is rising upwards. By this level, you should be able to easily know why it is always negative. So therefore, it means that v squared is equal to u squared minus 2g capital H. If I introduce a useful half m, I multiply by a half m throughout, I'll get R half mv squared is equal to R half mu squared minus mg capital H. Okay, there was a 2 there, but that 2 has been cancelled out by this 2 when there are half m. Therefore, R half mu squared, which is the initial kinetic energy, is going to be equal to R half mv squared plus mg capital H. This is total energy at B. This is total energy at A. Therefore, mechanical energy is always conserved. Why? Because total mechanical energy at A is equal to the mechanical energy at B. So they can ask you to prove that, even by condition, saying there is a particle projected from the ground, reaches a point B at a height h, prove that mechanical energy is conserved. Or they can ask you to prove if the body was projected from a height small h or small y above the ground. What if it was set in this case? They said, what if they say the particle was projected from a point A with initial velocity u, and this A was at a height small h. Then it reaches a point B with a velocity v, and at B it is going to be at a height y from the ground. You realize that if that is the case, then it would have traveled a distance from here, from A to B, which distance is y minus h. So this is the interpretation you have to put across when you have such a scenario. So for this reason, you can say at A, the particle possesses potential energy because it is slightly above the ground, which is mg what? H. At A, it also possesses kinetic what? Energy, which is a half mv squared. Then at B, the particle possesses kinetic energy and also possesses potential energy, which is mg of the height from A to B it has moved is mg what? It is mgy. Then the kinetic energy at B is a half mv squared. The one at A was mu squared. Therefore, they can ask you to prove the principle of conservation of mechanical energy. Still, we borrow from the third equation of motion, which is v squared is equal to u squared plus 2as. The height it would have covered from A is going to be y minus h. Because it's moving upwards, g is negative, so v squared is going to be equal to u squared minus 2g of y minus h. When I introduce a multiplication by a half m, I'll realize a half m v squared is equal to a half m u squared minus a half m times 2g into y minus h. I lose the 2 with this 2. Finally, I will have a half m v squared is equal to a half m u squared minus m g y plus m g h. When I collect the negative on the other side, I'll get a half m v squared plus m g y is equal to a half mu squared plus mgh. Now, when you look at a half mu squared plus mgh, it is here. This is the total energy at A. So this corresponds total energy at A. Then this corresponds to the total energy at B. Therefore, mechanical energy at A is equal to mechanical energy at B. Hence, we would have proved the principle of conservation of mechanical energy, even if the body was projected slightly above the ground or above a given reference. The person who has just come in, you are very late. For us, we are quiet. Now you're coming in with your noise. Abdi. Can you mute? So, this means that always total energy is supposed to be equal to what? The constant. And this is going to refer us back to the incline. When you go back to the incline, we saw that if a body was projected down here, and reached up there, overcoming a friction, projected with a velocity v, reaching here with a velocity 0, but having risen to a given height. Remember, we said h is equal to x sine theta. Then at A and B, the total energy should have been the same. Yeah. So the kinetic energy at A is going to be lost. But lost to what? It's going to be lost to work done against gravity. Plus, as we are moving up there, we are going to do work against friction. So the difference between the work done against friction and the work we have lost as kinetic energy will always give us the measure of the work done against gravity. Likewise, the work done against friction is the difference between the kinetic energy we had before and the potential energy we shall acquire later. So this is going to be RF mv squared is equal to mgh plus frictional force times x, because the distance x, the frictional force we have covered overcoming it, is what we have up there. So if I simplify this to RF mv squared is going to be equal to mg x sine of theta plus, remember I told you earlier, we had frictional force was where is it? Work done against friction is here. It is mg mu x cos theta. So we have mg mu x cos theta. When you divide everything by m, you will see that you have v squared is equal to 2gx sine theta plus 2 mu x g cos theta. So finally, v squared can be got from 2gx into sine of theta plus mu cos of theta. So if someone wants to find the speed with which the particle was projected to go up a rough inclined plane, one can use this expression. Even if you have not derived as far as this one, the most important statement was this equation statement, this one, for conservation of energy. If we have lost kinetic energy, what have we lost it to? We have lost it to 1, work done against friction. 2, we have also lost it to work done against gravity. So one can say work done against friction or work done against gravity is equal to the kinetic energy before minus the work done against frictional force. One can also always use this interpretation. Another one can use work done against friction is equal to the kinetic energy before minus the work done against gravity. All these boxes are correct equation statements we can use to follow these items on inclined planes and how energy is possessed. Okay. Any questions so far on these derivations? Because what is going to be left is the equations, is numbers to solve, then also to introduce power later. Any questions?
No questions.
Okay. So please go and review the notes I sent. I'm going to send other notes and other numbers. Any challenging numbers, send them to me, because now I don't want to teach a lot because now guys are not here. At least I had like 5 guys, I would have taught the whole topic because I was willing to give in 2 hours today. But since people are not here, but next week, this is going to be the last warning. Next week, I'll teach whoever is available until we finish. Because I intend to finish this off, then I introduce circular motion. Okay, because now I want to start something new, which people have not yet covered at all. So if no concerns, I think we can stop here for today.
So I want to take a screenshot of the first page.
You want to ask me on the first page?
Screenshot.
You want to take a screenshot? Okay.
Professor, thank you.